All right, today we are diving into something truly amazing. We're talking about how a powerful new AI is learning to decode a secret language, one that's hidden in the totally chaotic movement of tiny, tiny particles. It's really a story about learning to see the invisible and understand a dance that's happening all around us, on a scale we can't even imagine.
So, to get your head around this, just imagine a single nanoparticle as a dancer on a microscopic stage. We can watch its path, right? This beautiful, totally erratic dance that unfolds over time. But here's the big mystery. We can see the dance, but we can't see the dance floor or hear the music. We have no idea what forces are actually pushing and pulling this dancer to move in this specific way.
And that brings us to the absolute core question that scientists are desperately trying to answer. Is this incredibly intricate path just, random, meaningless noise? Or is there a deeper message hidden in all that motion? A message that could tell us everything about the invisible world these particles actually live in?
To even begin to answer that, we first need to get a handle on the technology that lets us watch this dance in the first place, and, of course, the pretty unique challenges it brings with it.
Okay, so this is liquid phase transmission electron microscopy, or LPTEM for short. It's a really remarkable technique that lets us peek into the liquid environment where nanoparticles do their thing. On the left, you can see the basic setup, this tiny little liquid cell chamber. And on the right, well, that's what the microscope actually sees, raw, noisy video. And from that, we can pull out those particle paths.
But here's the fundamental problem, the real kicker. Even with this incredible microscope, we can track a particle's path with mind-boggling precision. But all the complex, invisible forces that are acting on it, they're still a complete mystery. We can't see the stickiness of the liquid or the microscopic bumps on the surface it's dancing on.
And this, my friends, is where the hero of our story comes in. To solve this problem, researchers developed a specially designed AI model that can come at this problem from a totally new and frankly brilliant angle.
Meet Leonardo. Now, it's a generative AI, sure, but it's not designed to be just some simple imitator. Instead of just copying the dance moves step for step, Leonardo is way more like a sophisticated dance critic. It's been built to understand the style, the rhythm, the very essence of the movement itself.
Now don't worry, you don't need to understand every little detail here. The key thing is that Leonardo uses what's called a transformer-based architecture, which is just exceptionally good at capturing complex patterns over time. Perfect for understanding the rhythm of our nanoparticles dance.
And this right here is the absolute key innovation. Leonardo is a physics-informed AI. So instead of being rewarded for making a perfect carbon copy of a trajectory, it's graded on how well it recreates the statistical feel of the original. Things like the distribution of its steps, the correlations in its speed. These are the kinds of stats that actually represent the underlying physics of the environment. It's a whole new way of thinking.
You see, the old way would be to force the AI to make an exact copy. But for a random or stochastic system like this one, that's not only nearly impossible, it's not very useful. The Leonardo way is to aim for statistical likeness, to generate a brand new dance that has the exact same character and physical properties as the original. It's just a much, much smarter way to get at the physics underneath it all.
So, how does this all work in practice? Well, it's actually pretty straightforward. First, we show Leonardo a real trajectory from a real experiment. Then, we ask it to generate a completely new one, based on what it's learned. And finally, we compare the statistical style of the two dances to see just how well it did. And here you go, a side-by-side comparison. On the left, that's the real path from the experiment. And on the right, that's Leonardo's creation. Now you'll notice the paths aren't identical and they're not supposed to be, but they feel the same, don't they? They have the same chaotic energy, the same structure. This is how we know Leonardo actually succeeded.
Okay, so the generated dance looks good to us, but how do we know for sure? How can we prove objectively that Leonardo's creations are statistically indistinguishable from the real deal? For that, you need an expert judge. So the researchers brought in another AI, this one called Monet 2.0, to act as a totally impartial judge. Monet 2.0 is a classifier, and it was trained to be an expert at telling the difference between all kinds of nanoparticle motion. Think of it as being able to tell a waltz from a tango, just on a microscopic level. And this image, wow. This just brilliantly illustrates the final verdict. It's called a UMAP plot, which is just a fancy way to visualize really complex data. The yellow dots, those are the real trajectories. The green dots are Leonardo's creations. And as you can plainly see, the judge, Monet 2.0, sees them as occupying the exact same space. They are, for all intents and purposes, statistically inseparable. It couldn't tell them apart.
We can even put a number on it using a measure called freshet distance. The score between the real and the generated data was just 7.88. Now, to put that in perspective, the distance between other known types of motion is way higher. A lower score means they are more similar, which makes this an absolutely outstanding result.
So, let's get to the payoff. Now that we have an AI we can actually trust, one that truly gets the style of the dance, we can use it to interpret that dance. We can finally start to understand the invisible stage that these nanoparticles are performing on. And here's the crucial discovery. By analyzing thousands of these paths, Leonardo was able to describe the particle's environment using two main characteristics. First, heterogeneity, which you can just think of as the bumpiness of the surface it's moving on. And second, viscoelasticity, which is like the stickiness of the liquid, a kind of caging effect that can trap the particle for a moment.
This brand new understanding let researchers ask a really critical question. What happens to this invisible landscape if we start changing the experimental conditions? For instance, what if we crank up the intensity of the microscope's electron beam? Or what if we use a different sized particle? And Leonardo gave them the answer, loud and clear. It showed that when they turned up the electron beam's intensity, the energy landscape became more heterogeneous, or in other words, bumpier. This actually caused particles to get stuck in these little energy traps and then suddenly escape, creating a much more erratic, jumpy dance.
And it also made a pretty cool discovery about the particle size. Smaller nanoparticles it found experience stronger caging effects. It's almost as if the liquid around them becomes stickier, holding them back more than their bigger cousins. So the dance floor itself actually changes depending on the dancer. How cool is that?
So, after all of this, what's the big picture? What's the major takeaway from all this fascinating research?
Well, what we've seen is how a totally new kind of AI can watch a chaotic dance and literally learn the rules of the dance floor. And by focusing on that statistical style, it reveals invisible forces we could never see before. This matters so much because it gives scientists a powerful new tool, like a black box simulator, to understand and design things at the nanoscale. And that could mean everything from more efficient batteries to new ways of delivering drugs right where they need to go. And that really just leaves us with a final, kind of mind-blowing thought. We've just seen an AI learn the hidden physics of a world that is far too small for us to ever perceive directly. It really makes you wonder, what other invisible worlds, from the complex folding of proteins to the bizarre behavior of quantum materials, will this new generation of AI allow us to finally see?